Okay, so I'm going to start talking about chapter 20 in this video, and so I'm going to cover the first brief few slides with respect to chapter 20. The majority of this ideally is supposed to be kind of review, so I'm going to kind of go through it quickly. If you still have questions, though, please make sure to contact me or ask me if something doesn't necessarily make sense or you don't quite remember what I'm talking about. Okay, so chapter 20 is going to deal with this concept of electrochemistry. And so just overall, electrochemistry deals with chemical reactions that either produce or utilize electrical current. Right? So it's kind of like this broad description of a variety of different things that are based on the fact that certain chemical reactions can either utilize or produce electrical current. All right, so what is the basis behind electrochemistry and these types of chemical reactions that use electrical current? So the base behind this is something called redox reactions or oxidation reduction reactions. We tend to term these guys redox reactions for short, just a nice little abbreviated version of oxidation reduction. So you guys should have learned about oxidation reduction reactions in 151. So oxidation reduction reactions have electrons that are transferred between reactants. So that's essentially the characteristic of redox reactions. You have electrons that are being transferred between our various reactants, and that's a big hallmark of a redox reaction, right? So there are two different things that can occur in a redox reaction. The first one is termed oxidation, and the second one is reduction. So oxidation is where we have a loss of electrons. So if a reactant loses electrons to something else, that is what oxidation is. On the other hand, if we have a reduction, we have essentially something gaining electrons. So gain of electrons is reduction. And so you can generally remember that oxidation is loss of electrons, reduction is gain of electrons via our nice little acronym or whatever this is here. Leo the lion says GR. So Leo is loss of electrons is oxidation, and then GR is gain of electrons is reduction. So gain of electrons is reduction. So Leo the lion says GR. Okay. All right, so in 151, how did we determine whether or not something has lost an electron or something has gained an electron in a chemical reaction? And we use something called oxidation states. Okay, so just as a reminder, we learned how to assign oxidation states in chemical reactants, and being able to track oxidation states was the means by which we determined whether or not something was oxidized or reduced, right? So as a note here, just as a reminder, this is not an actual charge, right? So this is an imaginary type number, and we utilize it more as a bookkeeping method. So let me erase this. Right, so this is not an actual charge. It looks like a charge, but it's not a charge. And again, it's more of just a bookkeeping method for us to track electrons in a chemical reaction, okay? So it's a fictitious type of thing that we've kind of invented to help us in determining whether or not a redox reaction has occurred. So for example, let's look at this reaction down here where we have calcium metal reacting with liquid water to form calcium hydroxide and hydrogen gas. So if we go through and we assign oxidation states for this reaction, calcium here has an oxidation state of 0 as a reactant. When it goes over to the products, it changes oxidation states to a +2. So the only way that it could go from a 0 to a +2 oxidation state is having lost an electron, right? So if it loses an electron, we know that's oxidation. So calcium was oxidized here, whereas hydrogen goes from a +1 as a reactant. Right, so a +1 in the form of water, it goes to a 0 as a product. So the only way to go from a plus to a 0 is to gain an electron, which is a negative charge thing. So gain of electrons is reduction. All right, so in this reaction, by utilizing oxidation states, we found that calcium was oxidized, whereas hydrogen was reduced, okay? And so I can see going from 0 to a +2 as a loss of electrons, but this is also just an increase in oxidation state. So increase in oxidation state indicates loss of electrons, that's an oxidation, whereas for our little reduction over here, we go from a +1 to a 0. This is a decrease in oxidation state. So decrease in oxidation state, which is a hallmark of a reduction process. Okay, so again, these oxidation states are the means by which we were going to determine whether or not something was oxidized or reduced. So you may want to say, oh, well, how did you know that calcium was a 0 and then it went to a +2? So we did teach you how to assign oxidation states to things 151. So there were kind of like a nice little collection of rules that you were supposed to follow and how to assign oxidation states. So I'm going to briefly go over those rules in this slide. All right, so the first rule was that anything that was in the elemental form of that element or of that compound or whatever we're looking at, anything in the elemental form always had an oxidation state equal to 0. Okay, so these would have been things like calcium, solid, right? That is the elemental form of calcium. Same thing for things like sodium, solid, just plain normal elemental forms of these metals, as well as all of our diatomic elements. So these were things like hydrogen, diatomic oxygen, etc. Right? There are a lot of different diatomic elements. So all of these guys would have an oxidation state of 0 because, again, that is the elemental form of that atom. All right, so then the second rule was that any monoatomic ion, so what do I mean by monoatomic ion, was going to have an oxidation state that was equal to the overall charge of the ion. Right, so this would be something like a calcium 2+. This is what I mean by monoatomic. There's only one of them, so that's the monoatomic part. It is an ion. It has a charge to it. So its charge is 2+, right? And so its oxidation state is going to be a +2. With respect to oxidation states, we always write it as the sign and then the number, whereas when we write it as a charge, we always write it as the number and then the charge. Okay, so anything like that, so calcium 2+ has an oxidation state of +2. If we had something like chlorine minus, then the oxidation state here is, again, just the overall charge of the ion, which is 1 minus, or -1 in this case. Okay, so then the third one was if we have any type of compound. So any type of compound that means more than one element that's combining, the oxidation state of all the atoms in the compound has to sum to the overall charge of the compound. Compound has to equal the overall charge of the compound. Okay, so for example, let's say we had something like water. So liquid water, we have 2 hydrogens in this compound, we have 1 oxygen, and the overall charge here is 0. Okay, so when we summed up all of the atoms, or all the oxidation states of the atoms in this compound, it has to sum to the overall charge of the compound. So 2 times the oxidation state of hydrogen plus 1 times the oxidation state of oxygen has to equal 0, right? So this was a neutral compound. This was neutral. So again, they sum to 0. If we had a charged compound, though, something like maybe a polyatomic ion like nitrate, then again, the sum of these guys all has to sum to the overall charge of the compound, which is -1 in this case, right? So this would be 1 times the oxidation state of nitrogen plus 3 times the oxidation state of oxygen has to equal this overall -1 charge. And then the last one goes about how we actually assign oxidation states to these things when we're in compounds, right? So now if we want to assign the oxidation state to things, we're going to follow rule number 4. And in rule number 4 and 5, we're essentially going to do this in order of the order that takes precedent, right? So, for example, group number 4, the first rule is that any group 1 or group 2 metal, so that's the first two columns, column 1 versus column 2, we're going to give them just the overall normal charge of these guys. So any group 1 or group 2 metal, group 1 metal would have a +1 oxidation state. Group 2 metals have a +2 oxidation state. So those guys are the easiest to predict. They're the ones that come first. And then if we deal with nonmetals, so nonmetals, we're going to assign oxidation state in kind of this order. So fluorine is the most predictable. It's going to have an oxidation state of -1. And let me just get rid of this charge. So fluorine, hydrogen comes next. It's going to have an oxidation state of +1. Then oxygen has an oxidation state of -2. And then the remainder of group 7, which is all the halogens, they have a -1. Same thing with group 6. This is what lies below oxygen. These guys all have -2. And then we can move on to group 5, which has a -3 overall oxidation state, okay? So I'm just stating these. I know it doesn't necessarily make sense if you don't remember how to go about doing this, but hopefully when we utilize them, they will make a little bit more sense, right? So for example, if I want to assign oxidation states to these compounds, for the first one, I want to assign the oxidation state to chlorine, and this should be chlorine gas. Using my first rule, this is chlorine in its elemental form, right? And so because of that, chlorine here, Cl2 gas, has an oxidation state equal to 0. Because anything in its elemental form has an oxidation state equal to 0. Same thing for number 2. So number 2, we have sodium +1. This is a monoatomic ion, right? And so this goes back to rule number 2. Any type of monoatomic ion, the oxidation state is just going to be the overall charge of the ion. So the oxidation state for sodium +1 is just going to be +1. All right, so then in 3, we have our first compound. So this compound here is potassium fluoride. Note that it is neutral, so it's a neutral compound. So the rule in number 3 is that the oxidation state of potassium oxidation state of potassium plus the oxidation state of fluorine has to equal the overall charge of the compound, which is 0, right? So that's kind of like the idea behind 3. And then how do we know what the oxidation state of potassium, the oxidation state of fluorine is? Well, then we use rule 4. In rule 4, again, we're going to go in order of introduction. So group 1, group 2, we would assign first, and then we would assign the metals in this order afterwards. So potassium is a group 1 metal. Oops. So potassium is a group 1 metal. It is most predictable. So we're going to go ahead and assign its oxidation state first. So this is a +1 plus the oxidation state of fluorine. We'll just give that an X equals 0. So when we solve for this, we'll find that the oxidation state of fluorine is equal to a -1. Right? So it's the whole idea is that 3 has to be obeyed, so everything has to sum to the overall charge of the compound. But then who you get to assign first comes when we talk about rule 4, right? So group 1, group 2 metals trump or take precedent over all of the nonmetals. And so the nonmetal is going to take on the oxidation state needed to ensure that rule 3 is obeyed, that they sum to this overall charge of 0. So for potassium here, we're going to write our little oxidation states. So for potassium, oxidation state is a +1, and for fluorine, the oxidation state is a -1. Okay, So then CO2 is next. So CO2, this is 3, this is 4. So same thing. These guys overall sum to 0 because it's a neutral compound. So I have 1 carbon. So 1 times the oxidation state of carbon plus I have 2 oxygens, so 2 times the oxidation state of oxygen has to sum to the overall charge of the molecule. Now the question is, who will we assign first? Who takes precedent? Is it carbon or is it oxygen? And so when I go over to rule 4, I find that oxygen is up here and carbon, which is in group 4, is much farther below it. Right, so because of that, we know that oxygen will have an oxidation state of 2, and so carbon is going to take on whatever oxidation state it needs to satisfy rule 3, right? So we have this oxidation state of carbon. I'm going to represent this as some sort of unknown x, plus 2 times the oxidation state of oxygen, which is minus 2, is equal to 0. And again, I include the 2 because there are 2 oxygens in this compound. So now x plus a minus 4 equals 0. So the oxidation state of carbon is a positive 4. Okay, so we have a positive 4 oxidation state and a minus 2 for oxygen. We go ahead and complete that. We would have carbon as a positive 4, and then each oxygen is a minus 2. And then for the last one, same exact thing, except now we're dealing with a charged molecule, right? So I'm going to take my little 5 down here. We've got sulfate. So again, rule 3 has to be obeyed. So there's 1 sulfur. So 1 times the oxidation state of sulfur, plus there are 4 oxygens, so 4 times the oxidation state of oxygen, has to equal the overall charge of the molecule, which ends up being 2 here, minus 2. And again, if we go back to our list, we'll find that oxygen is more predictable, right? It comes up here, whereas sulfur is below oxygen in group 6, right? So sulfur is going to be dependent on what oxygen is, because oxygen is more predictable. It takes precedent in our little list here. And so then again, I'm going to assign this some sort of unknown x, plus 4 times the oxidation state of oxygen, which is a minus 2, is equal to minus 2 overall. So x plus a minus 8 is equal to minus 2. So x is equal to a positive 6. So in this compound, sulfur is equal to a plus 6, and then oxygen is equal to a minus 2. Okay, so that is just a reminder on how to assign oxidation states. Okay, so again, the purpose of assigning oxidation states to things is to be able to identify whether or not a redox process has occurred in a chemical reaction, and then not only to identify whether or not one has occurred, who has been oxidized and who has been reduced, right? So again, oxidation occurs when something has lost electrons. This usually, with respect to oxidation states, results in an increase in the oxidation state, right? So we usually see an increase in oxidation state with oxidation, whereas reduction results whenever we gain electrons, and so we always usually see the oxidation state decrease between the reactants to the products. And again, hopefully we'll illustrate this in the next example. Okay, so I'm going to utilize these oxidation states where we've just talked about the rules to identify whether or not, first off, whether or not we have a redox reaction, second, who's been oxidized and who has been reduced, okay? And so to do this, I'm going to go through and I'm going to assign the oxidation state to every atom in this chemical reaction, okay? I'm going to start on my left with tin, and so tin, this is tin solid. This is rule number 1 with respect to oxidation state, right? This is the elemental form of tin. So the oxidation state of tin here is 0. Now I'm going to move on to my next compound. With respect to oxidation states, we never really note the stoichiometric coefficient in front. We're only looking at the overall compound itself. And so I'm going to assign oxidation states to all of the atoms in this compound. We've got HNO3. It's a neutral molecule, so all of these guys have to sum to 0. And so I've got the oxidation state of hydrogen plus the oxidation state of nitrogen plus 3 times the oxidation state of oxygen. These guys all have to sum to 0. Now, if I go back to rule number 4, between hydrogen and nitrogen and oxygen, hydrogen is the most predictable. So I would assign hydrogen first. And if I look at that chart, hydrogen had an oxidation state of a +1. And then between nitrogen and oxygen, oxygen would again be the most predictable. It lies higher on that list. It has an oxidation state of -2. So this is going to be +1 times this unknown X, which stands for nitrogen, plus 3 times the -2 is equal to 0. And again, the way I kind of utilize this is I just go in order of that chart, but I go in order until I have one thing that's left to be assigned, right? So I assigned hydrogen first, I then assigned oxygen, and I let nitrogen be whatever it needed to be to satisfy this overall equation. The fact that these guys all need to sum to 0, okay? So when I add these guys all up, I have a +1 plus X, and then I have a -6 is equal to 0. So then X is going to be equal to a +5, okay? So here we have a +1 for hydrogen, a -2 for oxygen, and a +5 for nitrogen. So that's everyone, or those are the oxidation states of all of them on the reactant side. We will now move over to the products. And we'll start with SNO2. So SNO2 here, we've got a compound. So SNO2, it has an overall charge of 0. So these guys all have to sum to 0. So we have the oxidation state of 10 plus 2 times the oxidation state of oxygen is equal to 0. Again, between 10 and oxygen, oxygen is more predictable. It comes on that list, the non-metal list in Rule 4. It has an oxidation state of -2. So now we've got this unknown X plus 2 times -2 is equal to 0. So X has to be a +4. So we've got a +4 here and a -2 for oxygen. And again, whenever we assign these, it's for each individual atom. Okay, so same thing for these guys. We've got nitrogen, oxidation state of nitrogen, plus 2 times the oxidation state of oxygen. Between nitrogen and oxygen, oxygen is more predictable and has a -2 oxidation state. So to satisfy this, nitrogen has to be a +4. So we have a +4, -2 again. And then last one is water. So H2O. Again, these guys sum to the overall charge of the compound, which is 0. Hydrogen actually ends up being the most predictable one here. It has a +1 oxidation state. It lies just above oxygen on that chart. And so oxygen will take on whatever it needs to satisfy the fact that these guys have to sum to 0. So oxygen ends up being a -2 here. So we have a +1 and a -2. Okay, so that is assigning oxidation states. Now we're going to utilize them to figure out who has been oxidized and who has been reduced. So if we look, let's go back to black here. 10 goes from a 0 to a +4. Right, so it goes from a 0 to a +4 oxidation state. The only way for it to move from something that is neutral to +4 would be to lose electrons. And specifically to lose 4 electrons. We should go ahead and start talking about that. If we lose 4 electrons, that means that we have been oxidized. And then in determining who has been reduced, if we look around, hydrogen is a +1, hydrogen is also a +1, so nothing happened there. We have oxygen as a -2, oxygen is a -2 and a -2, so nothing's happened there. Nitrogen, on the other hand, has gone from a +5 to a positive 4, right? So we see an increase in, nope, wrong one. Positive 5 to positive 4 is a decrease in oxidation state, meaning that it has gained a negative charge. So to gain a negative charge, that means to gain electrons, which means you have been reduced. Okay, so again, with respect to oxidation, the only way to increase your oxidation state is to lose electrons, and so that's why we see with respect to the oxidation. The only way to decrease your oxidation state is to gain electrons, and that's why we see this guy as being reduced. So the answer here for what has been oxidized and what has been reduced, so tin has been oxidized, and then nitrogen has been reduced. And if we look at nitrogen, we saw that it gained an electron, and that particularly is it gained 1 electron. It went from a positive 5 to a positive 4. To do that, it has to gain just 1 electron. Okay, so go ahead and try this one on your own. This is a little bit easier. So I want you to identify who's been oxidized and who has been reduced in this redox reaction. And this most likely will be probably a question that I ask in the video assignment quiz, so I'm not going to give you the answer to it. But yeah, just go ahead and try this one, and it should be fairly obvious in who has been oxidized and who has been reduced. Okay, so what we're going to start talking about next is how to balance redox reactions. So we haven't necessarily talked about balancing redox reactions yet, or I usually don't. So the first step in learning how to balance redox reactions is splitting the overall reaction into what we call 2 separate half reactions. So half reactions are just going to essentially show what happens in either the oxidation or the reduction process, okay? So for example, if we had this reaction where we have aluminum solid combining with copper 2+, going to make aluminum 3+, and copper solid, we can see that aluminum goes from a 0 to a +3, so it's been oxidized, whereas copper has gone from a +2 to a 0, it's been reduced, right? If we wanted to take this reaction and write the 2 separate half reactions, just the oxidation and the reduction, we would first figure out, number 1, who's been oxidized, so that was aluminum, and then we'd also figure out how many electrons does aluminum actually lose, right? So in going from a 0 to a 3+ ion, it has to lose 3 electrons, okay? And so also note that in an oxidation, the process, the overall chemical reaction, is what produces the electrons, right? So for oxidations, we write electrons as products as a result of that, okay? So the oxidation half reaction for this process would be aluminum going to make aluminum 3+, and then 3 electrons. We would then identify the reduction. So in this one, we have copper 2+ gaining electrons to make copper solid. That gaining is specifically a +2 electrons to take it from this 2+ to 0. So with respect to reductions, when we write the reduction half reaction, we write the electrons as a reactant. It's part of the process in taking whatever we have and forming whatever new thing we're making, right? So for oxidations, we write the electrons as products, whereas for reductions, we write the electrons as reactants, okay? And we also have to note how many actual electrons are being lost and being gained. Okay, so then once we can write half reactions, how are we going to go about actually balancing redox reactions overall? So there are 2 parts to redox reactions that we have to be concerned about balancing. The first one is what we're normally used to with respect to balancing chemical reactions, and that's balancing with respect to mass, right? The second thing, and this is the newer thing, is we also have to balance with respect to charge, okay? So there's going to be a couple of rules that we're going to follow in learning how to actually balance these. So the first thing, or the first step in how to balance redox reactions, is we're again going to assign oxidation states to everything in the reaction so that we know what has been oxidized and what has been reduced. And we also know how many electrons have been lost for both the oxidation and gained for the reduction. Okay, we're then going to write out these separate half reactions. And again, we're going to write electrons as a product for oxidations and as a reactant for reductions. We're then going to balance each half reaction by mass. So again, it's best to like illustrate this to kind of demonstrate what I mean. But the first thing we're going to do is balance anything other than hydrogen and oxygen. We will then go back and balance oxygen by adding a water. And then we will add protons to balance H as needed. And just as a little note here, if this is done in a basic solution, we are then going to neutralize all the protons with hydroxide ions. We are then going to go back and balance the half reactions by charge. We will sum everything up, and then we'll check at the end to make sure everything is balanced. So let's utilize these little steps in a problem to illustrate what I mean by this, right? So we want to balance this reaction, this redox reactions, in an acidic solution. So that's an important thing to note here. So my first step in balancing a redox reaction is to assign oxidation states so that I know who has been oxidized and who has been reduced. So for this problem, we have copper. So copper as a solid. So this is the elemental form of copper. Its oxidation state is equal to 0. So that's number one. We've got our first reactant. Oxidation state equal to 0. I'm going to move on to my second reactant. We have NO3. So for NO3, 1 minus. Again, using our rules for oxidation states, nitrogen is least predictable. Oxygen lies higher up on the list of assigning oxidation states. So we'll let nitrogen be this unknown that we're assigning, plus 3 times minus 2, which is the oxidation state of oxygen, has to sum to a minus 1. So the oxidation state of nitrogen here is a positive 5. So we'll go ahead and write that positive 5. And then the oxidation state of oxygen is a minus 2. We'll move over to the product side. So we have copper 2 plus. This is rule number 2. It's just a monoatomic ion, and it's going to take on the same oxidation state as the overall charge of the ion. So this is a 2 plus, makes it a plus 2 with respect to oxidation state. And then for NO2, same idea, except now we sum to 0. So we've got this unknown for nitrogen, plus 2 times the oxidation state of oxygen equals 0. So nitrogen is a positive 4. So we've got a positive 4 and a minus 2. Okay, so now once I've done that, I need to identify who has been oxidized and who has been reduced. So copper goes from a 0 to a plus 2. We see an increase in oxidation state. Again, the only way to go from a 0 to a plus 2 is to lose electrons. And most importantly, we have lost 2 electrons. Okay, so this is our oxidation. And so now oxidations always have to be coupled with something being reduced. Those electrons can't just disappear. We have oxygen as a minus 2 and a minus 2, so nothing changes there. The nitrogen, though, goes from a positive 5 to a positive 4. So we see a decrease in oxidation state, which indicates a gain of electrons. And so that would indicate that we have a reduction. So nitrogen is the element that gets reduced here. Most importantly, though, it goes from a plus 5 to a plus 4, so we just get a plus 1 electron. Okay, so now that we've done that, we're going to write out the separate half reactions. So I'm going to write out the oxidation process first. Oxidation. So our oxidation half reaction is copper solid going to copper 2 plus 2 electrons. And then I'm going to write out the reduction half reaction. So we have NO3, and it's going to gain 1 electron, going to make NO2. Okay, so again, I identified how many electrons were lost in oxidations. Electrons are products. I identified how many electrons were gained, and in reduction, electrons are reactants. So that is the second step, right? So we figured out who was oxidized, who was reduced, and now we've written out the two half reactions. Now we're going to balance the half reactions with respect to mass. So I'm going to focus first on the oxidation half reaction. So we'll write ox down here. We've got copper solid going to copper 2 plus 2 electrons. And if we're looking at just mass, we'll note that there's a 1 in front of this copper. It is balanced by a 1 over here. And that is the only element with which we need to balance, right? So this guy is balanced already. So check. Now we'll go to the reduction half reaction. So for the reduction, we've got NO3 minus plus 1 electron going to make NO2 gas. So now we're going to first start by balancing everything but oxygen or hydrogen. So the only thing to balance there would be nitrogen and nitrogen. There's a 1 and a 1, so we're good here. We're then going to balance oxygen by adding water. So on the reactant side, we have 3 oxygens, whereas on the product side, we only have 2 oxygens. And so to balance the oxygens, I'm going to add a water over here. So now that gives me 3 oxygens. But the problem with that is I've introduced a hydrogen here. So now to balance hydrogen, I'm going to add H+. So I need 2 H+ over here to balance the hydrogen. So now everything should be good. I've got 1 nitrogen. Let me get my eraser and erase this, erase this. So for the reduction half reaction, I have 1 times nitrogen, I have 1 times nitrogen, I have 3 times oxygen, I have 3 times oxygen, and I also have 2 times hydrogen, and I have 2 times hydrogen. So that is good. That is balanced with respect to mass. Okay, so after balancing with respect to mass, now we're going to balance with respect to charge, okay? So I'm going to go ahead and rewrite these over here. We've got copper going to copper 2 plus 2 electrons. And now for the reduction, we've got a 2H plus an NO3 minus plus 1 electron going to make NO2 gas plus H2O. And so now everything's balanced with respect to mass. We just have to balance with respect to charge, okay? So at this point in time, we have a 2 electrons for our oxidation process and a 1 electron for our reduction process. These guys have to have equal numbers. So to do that, I'm just going to take my reduction, and I'm going to take the entire thing, and I'm going to multiply by 2 so that we have equal numbers of electrons being transferred. So that's going to turn into 4H plus 2 NO3 minus plus 2 electrons going to make 2 NO2 plus 2 H2O. Okay, and so I'm going to go ahead and just cross this guy out to show that we're done with it. It has turned into our new reduction process that has 2 electrons. And so now I'm going to take my oxidation and I'm going to add it to my reduction. So we're adding these guys. Note that I have 2 electrons here as a reactant. I have 2 electrons over here as a product. Those are going to cancel, and I'm going to be left with 4H plus, this guy, plus copper solid, this guy, plus 2 NO3 minus. It's going to go to make 2 NO2 gases plus a copper 2 plus 2 H2Os. Okay, and so once you're there, you may want to check to make sure all of your masses are good. So we've got 4 H pluses, we've got 4 H's, we've got a copper and a copper, we've got 2 nitrogens, and then 6 oxygens. We've got 4 plus 2, 6 oxygens. Okay, and so this is our balanced redox reaction. And importantly to note, this is in acidic solution. Okay. Okay, so in this second example, we're going to do the exact same thing. The only thing that's going to change, though, is that we're going to balance this in a basic solution. So there's one little additional step that we have to add in to take into account that this is a basic solution, but everything else is going to essentially remain the same in balancing redox reactions. Okay, so first step to do this, we're going to assign oxidation states to everything. We'll start with the ClO minus. So again, this is a compound. It has to sum to the overall charge of the compound, which is a -1 right now. Oxygen is more predictable than chlorine. It is going to have a -2 oxidation state, and so then chlorine will have a +1 oxidation state overall, because a +1 added to a -2 goes to -1. Okay, so we have a +1, a -2. Move on to chromium hydroxide. So chromium, we have OH4. This is going to sum to -1. Between chromium, oxygen, hydrogen, chromium is the least predictable, so we'll leave this as some sort of unknown X. This is going to be added to, we have 4 times the oxidation state of oxygen, which is a -2, plus 4 times the oxidation state of hydrogen, which is a +1. This has to sum overall to -1. So when you add those guys together, you get X equal to a +3. So chromium is a +3. We've got oxygen, which is a -2, and hydrogen, which is a +1. They go over to our products. We've got CrO4 2-. So again, chromium will be the unknown. It's least predictable. We have 4 oxygens, so 4 times -2. And this has to sum to -2 overall. So X is equal to a +6 here. So we have a +6 and then a -2. And then chlorine, this is a monatomic ion. It's just going to have the same oxidation state as its overall charge, so -1. Okay, so now we've assigned oxidation states. We can determine who's been oxidized and reduced. So chromium goes from a +3 to a +6. So it has increased its oxidation state. To do that, it has to have lost electrons. And most importantly, it lost 3 electrons. So this is our oxidation. And again, the 3 is the fact we have a +3, a +6. It needs to lose 3 electrons to get to +6. So we can do the same thing for the reduction. So oxygen is a -2, it's a -2. It doesn't change oxidation state. Chlorine, though, goes from a +1 to a -1. So we have a decrease in oxidation state, meaning we have gained electrons. And more particularly, it went from a +1 to a -1, so it had to have gained 2 electrons. Okay, so now we can split up our 2 half reactions. I'm going to write the oxidation over on the left. So our oxidation half reaction, we have oxidation. We have CrOH4- going to CrO4 2-. Let me make that better. 2-. And then again, if we have an oxidation, the electrons are a product, and more importantly, there are 3 of them for this reaction. And then I'll go ahead and write the reduction same way. So we'll write reduction over here. So the reduction half reaction, we have ClO-. And again, reductions, electrons are reactants. It's going to gain 2 electrons and make Cl minus. Okay, so now that we've written out the half reactions, we're going to balance each with respect to mass. So the first thing that we focus on with mass is anything besides hydrogen and oxygen. For this one, we have a chromium and a chromium. We both have one, or we have one on both sides, so that is balanced. Then we're going to move on to oxygen. So we have 4 times oxygen here, and we have 4 oxygens here, so that balances, that's good. The last thing is hydrogen, so we have 4 hydrogens on the reactant side. We have none on the product, so I'm going to add 4 protons to balance the hydrogen. But now this is the big difference, right? It says that we are in a basic solution, and so in a basic solution, we are going to add as many hydroxide or OH minus ions to both sides to get rid of any type of protons present, okay? So what I mean by that, we have 4 protons. What I'm going to do is I'm going to add 4 hydroxide ions to this side. But if I do that, I have to do it to the other side as well. So I'm going to also add 4 hydroxide ions to my reactant side. So I'm going to add those guys together. I have 4 OH minus plus a CrOH4 going to make CrO4 minus plus 3 electrons. But then when we combine these two, H plus OH gives us water. And again, it's going to give us 4 waters because we have 4 of each of those. Okay? All right, so that's the only little extra difference. However many H pluses you have, you need to add OH minus to both sides, an equivalent amount, to get rid of those and do this in a basic solution. Okay, so now that is balanced with respect to mass for the oxidation. I've got 4 oxygen, 8 oxygen overall. I've got 8 hydrogens. I've got a chromium and a chromium, so we're good there. Okay, so same thing, we'll go over here. First step, anything besides oxygen and hydrogen. I've got a chlorine and a chlorine, so that is balanced. I have 1 oxygen over here, so I'm going to balance that by adding a water liquid. And then I'm going to balance the hydrogens that I've added on the other side by adding an equivalent amount of protons. So I'm going to add 2 H pluses. Except now, again, we're in a basic solution. So to get rid of the H pluses, I have to add the same equivalent amount of OH minuses, but I have to do that to both sides. Oh, it's 2, pardon me. So 2 OH minus. Okay, so we added the water to balance the oxygens. We added the H pluses to balance the hydrogens. And now to get rid of those H pluses, we're going to add an equivalent amount of hydroxide ion. We have to do that to both sides. So now again, when these guys combine, we get 2 waters. So 2 H2Os. That's that. We get a ClO minus. We get 2 electrons going to make Cl minus plus an H2O plus 2 OH minuses. Okay, and so we should also note that we have 2 H2Os here, and we have an H2O here. So those guys, one of those is going to cancel. We'll go ahead, we'll get rid of this one and this guy in front. So now this is balanced with respect to mass. We've got 1 water left, a ClO minus, 2 electrons, a Cl, and then 2 OH minuses. And again, the only reason why I got rid of that is because anything that is on the reactants as well as the products are going to cancel one another. We had 1 H2O as a product, 2 as a reactant, so one of them will cancel. Okay, so that's balanced. So now we are ready to combine these guys. So now we have balanced everything with respect to mass. Now we need to go back and balance with respect to charge. And so one thing to note is that our oxidation process uses 3 electrons, or it loses 3 electrons. Our reduction process gains 2. These have to be equal, so we can balance the charges by multiplying each reaction by whatever number necessary, so that the number of electrons overall is the same. So 2 and 3, their least common multiple is 6. So I'm going to go ahead and I'm going to take this guy, my oxidation, I'm going to multiply it by 2, because 2 times 3 gets us to 6. And I'm going to take my reduction, I'm going to multiply everything by 3, because 3 times 2 gets us to 6. Okay, so then we'll go down with what's left. So for our oxidation, we'll start there. So 2 times 4 gives us 8 OH minuses plus 2 CrOH 4 minus goes to make 2 CrO4 2 minus plus 6 electrons plus 8 waters. And then reduction, same thing, except now we're taking 3 and multiplying it in. So we'll have 3 H2Os plus 3 ClO minuses plus 6 electrons goes to make 3 Cl minuses plus 6 OH minus. Okay. Alright, so then we're ready to combine these guys. So if we add them together, we're going to get a bunch of stuff that cancels. So number 1, the electrons will cancel. Alright, so we have 6 and 6. Those guys will go away. We have 3 waters as a reactant. We have 8 as a product over here. So these 3 will be gone, and we'll be left with 5 over here. We also have a bunch of OH minuses. We have 6 over here. We have 8 over here. These guys will be gone, and we'll be left with 2. And I think that's it. Okay, so then if we add everything together, overall, we'll be left with 2 OH minus plus 2 CrOH 4 minus plus 3 ClO minuses. And it's going to go to make 2 CrO4 2 minus plus 3 Cl minuses plus 5 H2Os. And then again, it would be smart to go ahead and check with respect to mass. So I've got 2 plus 4, 8, 10, 13 oxygens. I've got 8 plus 5, so 13 oxygens. I've got 2, 4, this is 8, 10 hydrogens. No, that is 4, that's 8, that's 10, yeah, 10 hydrogens. I've got 10 hydrogens. I've got a chromium, I've got 2 chromiums. I've got 2 chromiums. And then I've got 3 chlorines. I've got 3 chlorines. So everything balances with respect to mass. There's no protons in here, so we know that we have done this in a basic solution. That is the big indicator behind the OH minus. Okay, so that's balancing redox reactions in a basic solution. Everything is the exact same, except for we're going to add an equivalent amount of hydroxide to both sides anytime there's a proton to get rid of the proton and make this basic. Okay, so I'm going to go ahead and have you guys try this one on your own. So I want you to balance this redox reaction in an acidic solution. This will be on the video assignment quiz, so make sure that you follow all the steps correctly, and hopefully you'll get the right answer.